Ó Luís, esta sessão é a terceira ou é a quarta?
A quinta.
Hello everyone and welcome to the fifth session of the iCEBreak. Today we have Felismina Moreira presenting. She's a coordinator of the Biomark unit in the iCEB Porto. She has a background expertise in the area of biosensors and extensive expertise in the development of electrical biosensors by using new synthetic materials for the recognition of a wide range of target analytes. Today's talk will be about the biosensor applications in the medical field and food analysis. Felismina, please have the screen.
Sorry. Okay. Good morning to everyone. My name is Felismina Moreira. I'm researcher at Biomark iCEB, and I will present some examples of biosensing device applied in medical and food context. So I will start to present. Sorry, because it's not changing. I don't know why. I will start to present Biomark Sensor Research. Biomark is a research group located at Institute Superior of Engineering of Porto, iCEB. Biomark was founded by Professor Goretti Salles in 2010 with the help or support with some PhD students. And I'm included in this group of PhD students. I'm working with Professor Goretti Salles since 15 years ago. So in 2020, in the beginning of 2020, Professor Goretti Salles moves from University of Coimbra, and she built a new research group, Biomark Coimbra, UC, and I start coordinating the research activities in Porto. We are around 20 researchers, and Professor Goretti Salles continue collaborating with Biomark at iCEB. We are around 7 PhD researchers, 12 PhD students. We have some 7 external researchers. We have some undergraduate students, 5, and some bachelor and master researchers, 5. So what we do? We develop biosensors, a biosensing device applied to different areas, environment, food, and mainly in health. We work essentially with biomimetic material, and we integrate this biomimetic material with biosensing devices. One biosensor is composed by one support material. This support material could be one inert material, has cellulose, PET, ceramica, and glass. And in the specific case of electrochemical biosensing device, we apply one layer of one conductive material, but for other applications, we could use nanomaterials directly as a support material. On top of this support material, we mobilize one biorecognition layer. This biorecognition layer could be from natural or synthetic nature. The natural includes enzymes and antibodies, and synthetic nature, aptamers or molecular imprinting polymer, the well-known biomimetic materials. So the translation between the interaction between the biorecognition element and the analyte of interest is translated in one signal that could be optical, electrical mass, or other. In Biomark, we work with optical biosensors and electrical biosensors. So, the natural biorecognition elements, the well-known, the gold standard, the antibodies, enzymes, they show several advantages, everyone knows, in terms of sensitivity and selectivity. However, they show some disadvantage in terms of usability, stability, and price. One promising alternative is the biomimetic materials or plastic antibodies. So for the synthesis of the plastic antibodies, the synthesis consists in three main steps. The first step consists in interaction between the analyte, the target analyte, could be one protein, one bacteria, one metabolite, one antibiotic, etc., and monomers and cross-linkers, because it's a plastic antibody, yeah, is a synthetic one polymer. So the first step consists in the complexation, then the polymerization takes out with addition of one stimulus, electrical, could be photo, electropolymerization, or one radical R initiator. The next step consists in the template removal from the polymeric matrix, and we use different strategies as solvent, organic solvents, acids, bases, or enzymes. We use usually we use proteinase K or trypsin in the specific case of proteins, if the target molecule is one protein, and then we have the rebinding. So the biomimetic materials could be, or the plastic antibodies could be, are widely used in chromatography or could be used in chemosensors. One example of one biomimetic material sensitized to detect one antimicrobial, oxytetracycline, widely used in aquaculture, was the synthesis of we sensitize one plastic antibody by mixing the functional monomers, in this case methacrylic acid, acrylamide, and one cross-linker, ethylene glycol dimethacrylate. We dissolve these in the target analyte. We dissolve these compounds in one organic solvent, add the one initiator, in this case benzoyl peroxide, and submitted the solution to a heating process during 30 minutes at 80 degrees. After that, the biomimetic material is entrapped in one polymeric matrix, one PVC membrane, with one porogenic solvent, and we drop casted the membrane with the electroactive ingredient on top of one electrode. In this case, this electrode is formed. This electrode is one perspec. Sorry, something is missing. Yes, in this case we used one electrode that was fabricated for us in Biomark. We used one copper wire, one perspex tubes, and carbon has a conductive material, and the membrane was drop casted on top of this electrode. Was a very cheap device. So the electrochemical, the overall performance of the biosensor was studied by potentiometric transduction. Several parameters were optimized, has the composition of the membrane, the amount of the sensor, and the type of mediator solvent that was incorporated in the membrane, and the best operational features was obtained when we co-polymerize the material we polymerize material with methacrylic acid. When we use 10 milligrams of the sensor, and when we use orthophenyl octylator as a solvent mediator. We evaluated the change of potential against different concentrations of oxytetracycline. So usually, or in general, imprint small proteins, small compounds is quite easy, and usually we succeed in this kind of approach. But when we try to imprint proteins, is another story, because as we know, proteins are quite complex and lacking stability. So we need to be very careful in imprinting proteins. So several technologies or several techniques could be employed. We could imprint only the epitope of the molecule, the protein, but in Biomark, we use the surface imprinting as a technique. So I will give some examples. I will give 4 examples of how to imprinting protein by using different support materials. I will give one example of one work where we use silica beads for imprinting myoglobin, one cardiac biomarker. I will give another example by using carbon nanotubes and screen printed electrodes. We can use also quantum dots as a support material for imprint, or gold nanoparticles. Okay, in this work, the first step consisted in amination of silica beads. Next, we introduce aldehyde groups by mobilization with glutaraldehyde in order to protein attach covalently on the bead surface by establishing an imine group. Then the polymerization takeout by sol gel. And the last step consists in the template removal from the polymeric matrix by acetic acid treatment. Then the beads were incorporated in one PVC membrane and were drop casted in this kind of electrodes, one syringe electrode. It's a very simple. We have one syringe, one copper wire, and carbon ink as a conductive material for to build or construct the electrode. And the membrane were drop casted on top of this layer, and then applied. The detection was performed by potentiometric technique. And we measure the potential against different concentrations of the protein, in this case, the myoglobin. Another strategy was to develop one molecular imprinting polymer based on an hydrogel on top of the carbon nanotubes. So the first step consists in modification or oxidation of the carbon nanotubes for following covalent attachment of the protein. The polymerization was performed with acrylamide has a monomer, bisacrylamide has a cross-linker, ammonium persulfate has initiator, and the template removal was performed by means of oxalic acid. So we used also a very cheap and easy electrodes, easy system. Portanto, we entrapped the nanomaterial in one polymeric membrane based on PVC and one solvent mediator to allow the flow of the ions, and we immobilized the membrane on this, or drop cast on the electrodes, and we study the operational features of the sensor with the potentiometry technique. So another strategy could be to use gold screen printed electrodes as a support material. Here we work with gold, carbon nanotubes, graphene, and others screen printed electrodes. I will present one with gold screen printed electrodes. First step consisted in the protein bound on the gold surface. In this case, the polymerization was taken out or performed by one electrical stimulus, potential, and we used aminophenol has a monomer, and the template removal was performed by using proteinase K, that one enzyme was a more friendly and soft procedure. So the analytical performance of the biosensor were evaluated by square wave voltammetry, one electrochemical technique. And then we moved for when we tried to improve the procedure of the imprinting stage of protein, and we introduced a new concept. We developed a smart plastic antibody material. Then we used also gold screen printed electrodes as a support material. And the first step consists in the modification of the gold electrode with 1-TL with carboxylic functional groups. The next step consisted in the protein covalently attachment. And we introduced for the first time in our group labeled monomers, positively and negatively charged, that will establish the binding sites for the imprinting. So the polymerization starts with addition of the monomers and cross-linkers, in this case acrylamide and bisacrylamide and ammonium persulfate, and the template removal was performed by action of one enzyme, in this case proteinase K. So the analytical performance of the biosensor were evaluated by different electrochemical techniques. In this case, we used impedance and square wave voltammetry, and we achieved, when we compare with the previous work that I present here, we achieved lower limit of detection. We really could, we really were able to improve the operational features of the biosensor. So, in resume, we have some ongoing projects on Biomark, and we use these strategies and others. We are working also with antibodies, and aptamers has a biorecognition element. Now, currently, we have the two key pioneer projects. Is one Interreg, is one project of cooperation, in cooperation with the north, between Portugal and north of Spain. Here in Portugal, we are developing biosensors for screening Alzheimer biomarkers. We are working with Alzheimer biosensors applied to Alzheimer biomarkers since 2014, starts in my postdoc. So now we are trying to develop a multiplex sensor. The idea is to quantify or determine different biomarkers in the same time. This project was very mediatic in the last year because Alzheimer has, everyone knows, is a very challenging disease, and the people, everyone has interest in to know more, and they have the hope that the researchers could do something for to help the people with this disease. We have another ongoing project, is technical project. We are developing colorimetric test strips for monitoring the immunity against COVID disease. This work is ongoing. At this stage, we are preparing manuscripts, and we are preparing one patent. This project was very mediatic, sorry, project also, because the subject, COVID. We have here in Biomark iCEBreak, we have one collaborative protocol with the CINAMIL group from military academia, and we have the project CIPA, is Integrated Systems for Food Safety. Is a collaborative project with UTAD, the company B2 Cloud. The whole in iCEBreak, in Biomark, is to develop one biosensor, electrochemical biosensor to detect pathogens, Escherichia coli, in water. This working is ongoing. We have another recent project in collaboration with also with CINAMIL group, is also one project in cooperation with different institutions, Coimbra, etc., Coimbra, University of Lisbon. This consortium is quite big. So, and the rule in Biomark is to analyze treats, food treats, by spectroscopy Raman. So, and that's all, and thank you for your attention.
Thank you, Felismina, for this very interesting and complete presentation. We already have several questions from the audience. So...
I need to go to the chat?
No, I'll read. Yeah.
You read? Okay.
So, but first, before reading those, I have a question. So, what is the technology readiness level of the Alzheimer sensors? So, in which stage are you now?
Yeah, in this stage we are analyzing only synthetic samples. Yeah, synthetic samples, serum synthetic samples. We till now, yeah, we didn't move yet for real samples. I respond to the question?
Yes. So there are still a few years to go before this solution reaching the market, right?
Yes. No. It needs more time, more years. Yes.
Okay.
Yeah.
So there's sorry.
I was trying to say that these biomarkers are quite tricky to work with them. We work with amyloid or proteins, and they aggregate, so it's not simple and takes time. But we have already a lot of publications. with plastic antibodies, mainly with plastic antibodies in the past. Now we are working with immunosensors as a biorecognition element before to try to move quicker, because as I told in the beginning, the antibodies are the gold standards. To develop plastic antibodies is more challenging because we are mimicking the nature, and this is not easy. But we are moving, I think, well, quite well.
Okay, thank you. And thanks. So I'm having technological problems.
Okay,
yeah, I think that
let me try. Let me try if you can share the screen now.
Okay. So I think you already answered also one of the questions from the audience. How does your sensors detect Alzheimer's disease, and what biomarkers are detected?
So, yeah, we are working with also neurotransmitters.
Okay, how early?
Yeah, and biomarkers associated with neuroinflammation. We published this year one research work for the detection of interleukin 6, one biosensor based on plastic antibody. But our focus is tau protein and the amyloid. But we work with the other biomarkers, but they are not so specific. They are biomarkers associated with neurodegenerative diseases.
Yeah. Okay, and I also asked how early, but I think I saw in one of your slides, I think I saw 10 years, right?
Yeah, but okay, I'm not sure if it is really 10 years. What the literature says is that the levels of amyloid and tau protein, the presence in the cephalorrachidian, sorry, it's in English, cephalorrachidian fluid and blood, the levels start changing very early, 10 years before the patients develop the symptoms of the disease.
Okay, thanks. So another question now, aptamers, MIPs, antibodies, or peptides, which are the best ligands?
Which are the best biorecognition elements? Oh, depends. We have works and I don't know. Okay, for me it's a tricky question, because I work at 15 years old with molecular imprinting polymer. Yeah, it's challenging, yes, but I believe and I think that are very promising. Well, but the gold standard, I need to be honest, the gold standard are the immunosensors, antibodies, yeah. But the antibodies showed the problems that I told, right? Problems in terms of stability, price, and etc. So it's difficult. All of these biorecognition elements shows advantage and disadvantage. And we have been developing along these years in Biomark. Yeah, I've been working with Professor Goretti, as I told a long time ago, before Biomark exists, 15, and Biomark has 10 years old, and I'm working at 15 years old with biosensors. So I don't know. I don't know, because we have very good sensors. We develop very good with very outstanding operational features, yeah, limit of detection and sensitivity and selectivity with aptamer, and with, for example, one oligonucleotides for the detection, for example, microRNAs. Depends. Another question?
Okay, thank you very much. And I think we'll only have time for one more question, so I'll go for the top one. Thank you for your interesting presentation. Which are the main issues related with translation of these biosensors to commercial applications?
Yeah, first I think that the big difficulty is to find one company interested and to help us, yeah, and to buy our technology for to introduce in the market. If we found it will be easier. And validation, the problem of biosensors, especially in health. Food and the environment is easier. It's difficult because a lot of steps for validation, yeah, like that will take years, several years. But I think and I believe that this is the way. Yeah, we need to work in this line. So a lot of people ask me when your biosensors for Alzheimer will be in the market. It's not easy, and will depends. I think that okay, the research community knows, right? Depends of us, depends on companies, depends of validation. Sometimes I feel sad because there's questions comes from the common people that are not researchers, they don't understand, and they think that the biosensors will be ready tomorrow. I think that you understand, all of you, the reality.
Yeah, so yeah, so it seems your research on Alzheimer's seems promising, as well as COVID. And
yes, yeah, we are working a long time ago with different biomarkers. We have promising results, I believe, and to get more financial support, because I need more financial support for move on for the next step. It is because currently I established collaboration with Hospital de São João, Department of Neurology, but till now the truth is that we didn't try to test our biosensors in a real situation with Alzheimer's disease patients. But okay, I'm moving my work and my path in this direction. But I need time, more time.
Okay, thank you very much. We are now closing our session, so thank you everyone for attending this session. And next week we'll have another iCEBreak, but this time the PhD edition. And thank you, and see you everyone. Bye.
Thank you very much.